Welcome to the 18th Flow Seminar. My name is Samuel Horvat, and together with Peter Iftarik, Virginia Smith, Aurelien Bellet, and Dan Alistar, we are organizing Flow Seminar. For those of you who are attending for the first time, Flow Seminar stands for the Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. Yeah, this includes both theory and application in areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization, systems, hardware, and so on. For today's talk, it's my great pleasure to introduce you our speaker, Wenting Zheng. So Wenting is currently a postdoc in the UC Berkeley RISE Lab, working with Raluca Adapova, and she will join CMU's computer science department as an assistant professor in fall 2021. She's broadly interested in system security and applied cryptography, and her recent research interests are in building practical systems for enabling secure collaborative computation. And today she's going to talk about her work on secure collaborative learning. So Wenting, the stage is yours.
Great, thank you for the introduction. And yeah, I'm very happy to be here virtually. And yeah, today I'm going to talk to you a bit about the research I did during graduate school on this concept of sharing without showing, or how to build systems that enable secure. Recently, there has been a need for collaborative learning because machine learning, right, is widely used by organizations to extract a tremendous amount of value out of their collected data. But at the same time, right, while there has been a lot of development in the machine learning analytics techniques, there's still a pretty glaring problem in that acquiring high quality data is actually pretty difficult for these organizations. And in fact, in many applications, the organizations need data that reside across different companies, different hospitals, for example. So here we really have this tension, right, where the applications need a huge amount of high quality data, but at the same time, organizations cannot share this sensitive data with each other. Right, and we illustrate this tension by going through two real world use cases that we encountered. The first one is anti-money laundering use case, where here we have a bank who wants to use analytics and machine learning to detect money laundering activities. But by the definition of money laundering, what happens is that criminals try to conceal their illegal activities by kind of laundering their money on committing transactions across many banks. So really, in order to actually compute an accurate result to accurately detect money laundering activities, one would need to compute on customer transaction data that's collected from multiple of these banks. But currently, this cannot really be done, right? Because the banks are not willing, rather, to share their customer transaction data with each other due to the fact that they are still competing with each other. In fact, here I have a quote from the chief risk officer of Scotiabank, one of the big Canadian banks that we're actually working with, collaborating with right now. I'm coming back to that later. But basically, he said that in the future, collaboration would be vital, and by doing so, it will really enhance yields by orders of magnitude. So that's one financial example. The next example is a flu outbreak prediction example. So here we have annual flu outbreaks in California, and we have medical organizations that want to predict locations of these outbreaks before they happen, right? So that you can distribute vaccines to these places more effectively. And in order to actually compute an accurate flu outbreak prediction model, then it would require, again, right, in this case, access to kind of patient data, in this case, collected from multiple hospitals across California. But currently, this cannot be done due to the fact that patient data is very sensitive. So these parties are, or these hospitals cannot share this patient data with each other due to policy regulation. So as you can see, right, there's really, you know, not only those two examples, but other examples that we have encountered, telecom to a nuclear facility auditing, that really would be enabled if we, that can be enabled by data sharing, but currently cannot be done today due to the fact that, you know, these parties, organizations, entities need to share sensitive data with each other, and they're unwilling or unable to do so. So one possible solution, right, is to, you know, we could leverage a trusted third party to do so, where these entities, they give their private data to this trusted third party, who just sees all the plain text data and then computes a result, I guess, for these entities. But you know, we feel that it's and you know, we've been talking to industry collaborators about this as well. It's not a great solution because you would need to put a lot of trust, right, in this trusted third party. So one extra party that you have to trust. Utilizing a trusted third party can be quite expensive. And also a trusted third party that sees all the plain text data, right, that's collected from all these different entities. Actually, they're concerned from their perspective, they're concerned about liability because they, you know, become a kind of a central target for attack. So so that's the kind of problem we want to solve. The problem we want to solve is to enable secure collaborative learning, but without using a trusted third party that sees all of the plain text data, right? And the approach, right, that I've been using in my graduate research is really to do so via a co-design of systems and cryptography, and really by kind of combining techniques from both areas, I'm able to build systems that provide strong and provable security guarantees, and also are often orders of magnitude faster than the more kind of straightforward approaches of combining these two areas together. So those are kind of the general technique, right? We want to combine systems with crypto, but what kind of security guarantees do we actually want to achieve, right? So we want to, right, what does sharing without showing mean, right? So we want to make sure that the computation is done, right, without using a trusted third party that sees all the plain text data. And additionally, right, we want to, actually from the participant's perspective, we want to make sure that the participants should only learn the final result of the computation and none of the intermediate results. Right, so this really corresponds to what is a model in, I guess, crypto as this ideal trusted third party, where in the ideal world, right, the parties just give their data to this, you know, trusted third party, but, you know, not a physical trusted third party, and then they only get the result at the end. So they don't see any of the intermediate results. And this is actually, this kind of security guarantee is actually a bit different from the traditional federated learning approaches that we've seen, which actually, you know, people end up sharing intermediate results, intermediate gradients, or sharing the kind of the aggregated gradients with each other. So there's some, you know, intermediate information leakage in those kinds of techniques. Okay, so how do we actually enable this kind of ideal trusted third party guarantee, right? So there are two major approaches, right? Two major techniques that people have used. One is more on the cryptography side, right? Where people use something called a secure multi-party computation, or MPC for short, to help enable this collaborative learning. And on the other hand, right, if you there's also something called a hardware enclaves, like Intel SGX, that enable this kind of computation. So secure multi-party computation, right? The cryptographic approach is a purely self-based approach. Basically, you have parties here, right? Different parties that jointly compute this function f with each other. Without any party learning the data of any other party beyond the function result, right? And really, what all they're doing is that, so it's a decentralized computation, and all they're doing is they exchange encrypted data with each other, and they also compute on this encrypted data, right? So all the data is encrypted, and they know their own data, and then at the end of the result, the end of computation, they learn the final result. So that's one approach, right? One popular approach. And the second popular approach is via the use of hardware enclave. So with some, more hardware assumption, but these enclaves have become widely available. So basically what an enclave is that it's a secure region in memory protected by the hardware, right? And so within this region, the CPU is also trusted, and within this region, you can load secret data as well as code, right? The code that you want to run, arbitrary code that you want to run in this environment. And an important feature that's provided by enclaves is this feature called remote attestation that allows the client to kind of remotely attest that the correct piece of code and correct state has been loaded into the enclave. And then after that, you can do some key exchange protocol to establish a secure channel with the enclave. And then also, the client can basically, the enclave is now kind of extension of the client, right? Extension of this trust environment. And then once it has the key from the client, then it can just do arbitrary computation on the client's encrypted data. Right, all within an untrusted operating system environment, right, on this remote machine. Right, so there are two of these approaches, right? They are quite different from each other, I would say. But so why do we really need these two approaches, right? As it turns out, they have different trade-offs, right? So from the cryptography side, right, it doesn't require federalized hardware, right? You can just run it on your normal everyday machines. But it does, because it's this more decentralized approach, it does require some kind of compute at every client. And it's also because you're using pure cryptography, right? It is relatively slow and can be quite expensive for bigger data sets, right? Compared to the hardware enclaves, which, it does, compared to crypto, it does require trusted hardware. It has actually, it's prone, I'm sure all of you have heard about this, it is prone to a side channel leakage, including something called access pattern leakage. That's, that a lot of existing attacks on SGX actually rely on. But on the other hand, it is very fast. You can run basically arbitrary code in it. And so, in the end, I think that both of these approaches are very viable, right? And very important. And so that's why this time I'm actually going to present two works, one on the crypto side and one on the more hardware enclave side. So on the crypto side, it's a work called Helen, which does a secure training for regularized linear models using secure multi-party computation. And for the hardware enclaves approach, I'm going to present secure XGBoost, which is does XGBoost, distribute XGBoost training and inference inside enclaves. But the one interesting property is that it's oblivious. And what this means is that it can actually protect against a large set of side channel attacks that are based on access patterns. So I will first talk about Helen, which is a joint work with my advisors, Ruka and Yang, as well as Joey from the Berkeley Rise Lab. So, so Helen uses MPC, right? So in terms of and I briefly talked about the kind of security guarantees that MPC provides, but kind of going into more detail, what does let's say that, the money laundering use case from before, right? The banks, they want to kind of, detect money laundering, right? Using their customer transaction data. What are the kind of the ideal security guarantees that the banks actually want to have, right? From the tool. So from the bank's perspective, right, it wants to make sure that whatever crypto protocol it runs, right, the protocol should be secure even if all of the other banks can collude with each other, right? So this is what we call a dishonest majority assumption in security. And it also, at the same time, wants to make sure that the protocol is secure, even if the adversary can potentially deviate from the protocol. And this is what we call malicious security. So basically, really what the bank wants is that it wants to just trust itself, right? Even in spite of what the other banks could potentially do. Right, so therefore it's dishonest security as well as what we call malicious security, right? We want to defend against a malicious attacker. So in terms of the prior work, right, if you take a look at the prior work in this secure collaborative learning area, as it turns out, most of them really do not satisfy these two properties. So dishonest majority among P parties, right, where you can have multiple of these parties, that often does not happen because prior works often just focus on collaboratively enabling collaborative learning among two parties only. And in terms of the malicious security, in fact, many of them actually rely on what protection against an adversary that's more semi-honest or honest but curious. So basically, an adversary that's kind of and more of an eavesdropper instead of an actual active attacker. So as we can see, there is a set of work, right, prior work that actually at the bottom here that actually do, satisfy these two important guarantees, and that is something what we call a generic platform for a generic maliciously secure MPC platform like Speed. So it's able to run any functionality, and it has very strong security guarantees. But the challenge here is that utilizing such a generic MPC, right, for your learning tasks can be very expensive due to expensive compute, very expensive communication, and really, every party needs to participate in the entire computation, even if you have some set of compute tasks that can be done at a single party locally, right, during the compute. So in fact, right, we kind of try to test it out, right? We try to run stochastic gradient descent for Lasso, right, a type of regularized linear model using such a generic maliciously secure MPC framework. And as it turns out, for 4 parties, each party has 100,000 samples of party, and the data set has 90 features. We actually estimated it would take 3 months to train this model. We couldn't actually run it, right? Because it actually ran out of memory way earlier. So the question that we want to ask is, can we actually design a more efficient protocol just for regularized linear models for now, right? And the answer is yes, a much more efficient protocol, right? And the insight here is that, instead of using such a generic platform, we really can, we really have to design specialized protocols that enable, in this case, right, for regularized linear models, to enable the cryptographic computation to scale independently of the number of training samples that the parties have, while still maintaining the same functionality and security guarantees of the protocol, right? So with this kind of, with our approaches, we're able to kind of reduce the estimated 3 months of training time to less than 3 hours, where we could actually run it and get a final model at the end. So how do we actually design such a specialized protocol, right? And there are 2 main techniques that we used. One is, right, we have an alternative formulation of the problem such that the cryptographic computation can be made more scalable. And this alternative formulation is in terms of both the data, right, the training data, as well as the algorithm itself. And for technique number 2, right, after we have expressed our computation and data in this alternative format, then we also split the secure computation into kind of a single party plain text computation. So everything is just run in plain text. Single party encrypted computation, right? That's kind of localized to one party. And then the rest of the computation that we have to, we have to do it in more generic MPC, where everybody is communicating with everybody. With, we push that into generic MPC, but we're able to split a large chunk of the computation into these more lightweight primitives, right? And of course, still maintaining functionality and security guarantees. So now I'm going to kind of walk through in more detail some of the, how we actually managed to, have alternative formulations as well as splitting the computation. Right. So as input, right, we have set of training data, n by d, that's input by every party. And n is number of samples that each party has, and d is the dimension of the data set. And here we're assuming that we're making assumption that n is much greater than d, which is actually true for many of the data sets that we observed, right? So the first problem, right, in designing such a secure protocol is that SGD is not very scalable in MPC at all. And in fact, right, what SGD does is essentially, I mean, simplify things a bit, but basically it kind of requires the parties to scan their training data, right? And so if you were to put SGD directly into MPC, then that can be very expensive because it has to scan the entire training data set and then also train on it inside MPC. So the first step that we took was to reformulate the stochastic gradient descent, right? To actually, instead of using SGD, you identified the ADMM, which is a not so commonly used as far as I know training algorithm that when you express regularized linear models using in this kind of training algorithm, it basically transforms to this iterative training on small pre-computed summary. So basically what happens in the plain text is that each party pre-computes a small summary of its input data, and then all parties iteratively train on these summaries. And the parties will end up converging in very few iterations compared to SGD, which has many iterations. So with this, right, so with this first alternative formulation, we can kind of design a Strawman MPC protocol that simply, puts where you simply put ADMM in MPC, right, where now each party pre-computes in plain text at locally, right, because it only needs to pre-compute the summary using its own data. So technically, right, if you intuitively, you shouldn't have to exchange or you shouldn't have to put that in secure computation yet. And after that is done, then you can have iterative computation that's executed by all of the parties in MPC, right, using these small summaries. So the Strawman MPC design, while it's actually efficient and secure if we had a semi-honest or honest but curious attacker, but it's actually only a partial and insecure solution if we want to defend against a malicious attacker. And the reason is that this kind of pre-computation, right, where each party pre-computes a summary, is actually quite tricky under the malicious setting. And the problem here is that summary creation cannot be directly pre-computed in plain text by each party. Just because, right, if you have a malicious party, then it can actually incorrectly pre-compute the summary. And in fact, it can actually just put into the MPC later as input a wrong summary. It's just maybe just a, made up of kind of a random inputs, such that the summary cannot be mapped to any of the valid inputs, training inputs that this party could have had, which in this case, because there is no mapping here, then it kind of violates this ideal trusted third-party model that we wanted to stick to, I guess. So therefore, we somehow have to make sure that this pre-computation, right, this computation of this the summary computation also needs to be somehow proven or verified officially, right? So there are two kind of steps to solving this problem. The first is only a partial solution, is that we can use something called zero knowledge proofs to actually have each party pre-compute the summary using its own data, right? Still doing that locally at each party, but then they need to add an additional step, right, to prove this summary computation. using zero-knowledge proofs, which are basically cryptographic proofs that allow a party to approve a party, right, to prove to a verifier party certain properties of the prover's computation are satisfied, but without revealing the prover's private inputs, right? And the verifier can also verify these proofs to, you know, to have confidence that the prover did indeed do these computations correctly. So then, right, using some zero-knowledge proof, custom zero-knowledge proof gadgets that we designed in the paper, each party, right, can simply pre-compute its summary in plain text, but then also prove the summary computation in zero-knowledge, and then the parties can, then every other party can simply verify this this property, right? So with this, we can still allow the parties to, we can still maintain this summary pre-computation such that each party executes it individually instead of jointly with every other party. But the problem is that the summary pre-computation is actually quite expensive still, because summary pre-computation and the proof rather is quite expensive because the proof needs to take in the entire training data set, right? Which again is very big. It has a large number of training samples. So here, right, we actually have an right, the second step, right, to reducing to improving the efficiency of this step is to actually have an alternate formulation of the input data, right? Where instead of using the original inputs and use that to prove the summary, well, we realized that we can actually reformulate the input data in such a way so that we can find smaller inputs that can still be used to kind of preserve the summary, right? So with this transformation from original inputs, large input, to reformulated small inputs, right? And then you can use that to compute the summary directly. Then what we can do is simply we can, first of all, directly prove the properties of the smaller inputs, right? So that we have to ensure that the smaller inputs still correspond to the larger original inputs. And then after that, we will then prove the summary generation from these smaller inputs, reformulated smaller inputs, so that both of these proofs are quite small and do not depend on the size of the original input, right? So in Helen, because for this regularized linear model training, we ended up we discovered that actually SVD can be used to reveal these small alternative formulation of the input data to still preserve the summary. So what we do is simply we use, instead of putting everything in zero-knowledge proofs, we first transform the data using SVD into new and smaller inputs, and then use those new and smaller inputs to compute the summary, right? And the proof is simply, we prove that the SVD transformation, or that rather that the new and smaller inputs can correspond to some input data that's chosen by the adversary, and then we also prove that the summary is generated correctly. So with this, alternative formulation of the input data, right? Then the proof size no longer needs to depend on n, which is quite large. So here I'm just going to quickly go through the evaluation. In terms of the experiment setup, we had we ran experiments on 4 parties on EC2. 2 are located in Oregon and 2 in Northern Virginia. And the baseline here is SGD implemented in SPIES. And in terms of training assumptions, right, we assume that SGD it has many trainings, or both have the same set of training samples, but due to the way the algorithm works, it has to scan off the data. And we experimentally found the number of iterations using multiple training data sets, the number of iterations that ADMM algorithm can converge. And we fix the number of iterations for ADMM. So in terms of evaluation here, we see a data set, a song prediction data set from I'll take it from UCI, which is a data set that has 90 features. And on the x-axis, we are scaling the number of samples per party, training samples per party. And on the y-axis, we have the runtime, right? So for the blue line, right, it's the estimate baseline. We can see that it scales linearly, right? The runtime increases linearly as you scan, or as the parties have more training data. Whereas the green line shows Helen's performance. And as you can see, it basically actually stays constant as you increase the number of samples per party. But that's, in reality, it does scale up very slowly, but because we're able to actually push the part of the computation that depends on the number of samples, training samples per party, to the plain text computation. The rest of the crypto computation does not depend on the number of training samples at all. So, and therefore you see this near constant behavior. And that roughly translates to a 900x performance gain when you have 100,000 samples per party. Yeah, so I'm going to, I guess, quickly stop here and see if people have questions about Helen before I move on to secure XGBoost.
So it seems there are no questions. We can continue.
Okay, sounds good. Okay, so now that's kind of the approach, the more cryptographic approach, and now I'm going to kind of dive down into hardware enclave-based approach, which and I'll talk about secure XGBoost, which is basically distributed XGBoost training and inference using enclaves, and at the same time, it also protects against access pattern leakage, right? So that's what Oblivious here means. So in terms of using enclaves, right, I briefly went over the properties with secure enclaves. And as it turns out, using, compared to, right, the crypto approach where everybody is just computing with each other in a decentralized way, doing collaborative learning using enclaves on the cloud is actually a very attractive option, because there are many actually multiple cloud providers that now provide hardware enclaves, just either bare machine ones or bare metal machines or virtual machines. And it's very exciting because it means that it provides everybody with much easier access to the hardware, and also really the parties can take advantage of the elastic compute resources provided by the cloud, right? So now this model, right, in this model, what happens is that you have multiple parties, right? They each encrypt their data and then give the cloud their encrypted data sets, and then the enclaves, right, on the cloud, which are basically, right, these isolated environments. Then the enclaves can do remote attestation, or I guess the clients can do remote attestation with the enclaves in the cloud, and give the enclaves its secret keys, and then the enclaves can just do arbitrary computation, right? Yeah, so the problem is that, sure, while the enclaves can run basically any binary, the problem is still that there's a data access pattern leakage, right, or side channel leakage, right, from these enclaves. And really, just by observing the sequence of memory accesses by the enclave, right, because again, right, the operating system itself can be malicious, and also by observing kind of the network traffic pattern, right? Like who's sending to which machine, sending to which machine, and how many bytes are being sent, then you can actually learn a lot of information about the underlying encrypted data. So, so in this project, we really try to kind of design and distribute XGBoost training and inference using, right, the XGBoost code, but then design in such a way such that it has a protection from this memory and network-based access pattern leakage. And XGBoost, as we all know, is a very popular machine learning framework, and basically what it is a gradient boosted decision tree, and it basically during training it constructs a tree ensembles, and then during the prediction, you take whichever prediction sample that you want to predict on, you use those samples and walk down the trees in order to get the once you reach a leaf node, you reach basically the leaf node represents the decision values, and then you can, for every one of these trees, you can sum up these decision values to reach a final decision, right? So, as it turns out, any kind of tree-based, I guess, training and inference, there's actually a lot of leakage. Just because, for example, right, during tree training, what happens is that this data set is partitioned at each node, and repartition as you kind of expand the nodes, etc. And so there's actually a lot of the memory access patterns are very data dependent, and the access patterns will end up leaking basically the ordering information about the ordering of data items, as well as the shape of the tree, right? So from these kinds of patterns, you can kind of learn information about the underlying encrypted training data, right? So what we did in this project is we designed Oblivious versions of the XGBoost training as well as inference algorithms. First of all, using these set of Oblivious primitives. So for comparison, array assignment, sorting, as well as array access, right? And using these primitives, we can actually construct efficient Oblivious algorithms, Oblivious versions of these training and inference algorithms. So, for example, right, going back to the tree training, what happens is that we first design an Oblivious single node addition algorithm that basically kind of follows the XGBoost algorithm as well. But it's first computes a histogram for each feature using our Oblivious primitives, O_access and O_assign. And then the parties or the machines broadcast and sums up these histograms. And then we partition the data based on the split value by assigning a marker for sample only using O_assign instead of kind of actually partitioning these samples together. So every time basically we do either broadcast or scans overall of the data, and so those are Oblivious. And while we can, so we have this node Oblivious node addition algorithm that we designed. While we can call that for every single node, we are actually have a more efficient way of combining these together by grouping these node addition via Oblivious level-wise training. So we do a single level of the tree each time by scanning through all of the training samples. And with this, we're actually able to always scan, right, the entire training data set for every level. And we're also able to construct a tree with some dummy nodes in there, but we are able to construct a tree that's kind of independent of the data input, so that from the tree structure, it does not actually leak information about the underlying training data, right? Right, so that's a very brief overview of our Oblivious XGBoost platform. And here I'm going to highlight some of the open source effort, right, that we have been devoting time into, because we really want to make our platforms real and usable by a lot of the by everybody, right? So in terms of for example, in terms of the cryptography side, right, we have a cryptographic execution engine. I only talk about Helen, right, which tackles linear models, but really we have a bunch of other projects that does convolutional neural network inference, as well as secure SQL, right? And on the hardware enclave side, I talk about secure XGBoost, but we also have so basically hardware enclave side, our goal is to not just put things in enclaves, right, but really fortify enclave execution engine so that it has protection against these access pattern-based leakage. So yeah, so I talk about secure XGBoost, but we also have a project called Opaque, which does Spark, which is able to enable Oblivious Spark SQL. Right, so we have both of these in terms of execution. We have both crypto as well as hardware enclaves based approaches. But on top of that, we're really hoping to create a unified Python API that the anybody can use, right? So you just program in Python, but then your program can be kind of translated into our execution backends. We also want to add a policy engine at this layer so that you can have an interesting privacy policy, and I'll actually talk a little bit about that later. And of course, with this unified Python API, we hope that many applications can be implemented. So our open source effort is here, is at this link on GitHub, and so we have many different kinds of projects on there, and we have actually collaborated with a bunch of companies and organizations, from IBM Research to Alibaba, etc. And actually, we do have a exciting collaboration with Ant Financial on credit scoring assessment, and as well as Scotiabank with a Scotiabank Microsoft on anti-money laundering detection. So, right, with these works, right, what's next, right? So, in terms of the MPC and crypto side, the question to answer is really, how to achieve better performance under a different a set of a variety of threat models for more and more complex functionality. So, can we go beyond, simple training and actually push it all the way to something crazy like neural network training, right? On the enclave side, right, the question really is how do we design it so that you can achieve better protection against side channel leakage and for generic programs. And I think one thing that could be interesting to the people, machine learning folks is, how to deal with parties with complex incentives and constraints, right? So here, right, we kind of going back to this, let's say, money laundering example where we have multiple banks that want to compute a model together, right? They are kind of concerned about various things, right? So while MPC or hardware enclaves, it can give you very strong security guarantees such that nothing is really leaks other than, or nothing is revealed rather, other than the final result. There's still many questions, right? Because the model, all the parties get the plain text model at the end. So the parties now are kind of concerned, right? What if the global model is really not what the parties want, right? So what if, let's say in this case, right, the global model only improves other parties' accuracies, but then this party is kind of left hanging, right? What if the global model actually embeds, from the privacy perspective, right? What if the global model actually embeds too much information about this party's training data? And what if the other parties, let's say this party, maybe the party is actually contributing some garbage input into the computation so that it's getting more out of this secure collaboration than this innocent party, right? So there are some initial ideas, for example, from the crypto side, right? What MPC can do is can enable kind of policies of some sorts, right? Because it can enable users to kind of design some policies such that the result is only released if the policy is satisfied. And in fact, you can even design such a way so that it releases different results to different parties depending on the kind of the policies that you design. So the different policies, there could be different policies. One example policy would be, differential privacy, right? Another example policy could be you can set an accuracy threshold so that if so that you also put into, as part of training protocol, a validation protocol that validates the model at the end in MPC, right? Using your validation data set such that if the model doesn't actually exceed a certain threshold, then you just don't release it to anybody, right? So, but of course, those are kind of simple examples of policies. The question still here is how do we actually, how to correctly model each party's incentives and constraints, right? Both the economic ones as well as privacy ones. How do we design policies to incentivize this collaboration instead of, having some parties being very afraid to commit their data, right? And just one last thought, from the crypto side, maybe we can look into MPC with, instead of with malicious adversaries, what about rational adversaries, right? So they have some kind of utilities that they want to achieve. Yeah, so I think those are kind of interesting questions to be answered jointly, in collaboration with the machine learning folks to really understand, the types of models that are being used and what kind of properties that they have. Yeah, so that's kind of the end. Oh, sorry, I guess one last thing, but basically very similar to what I said before, right? How do we make the parties accountable for their malicious inputs or potentially malicious inputs? So that if somebody inputs a garbage data, then we can track that party down. Okay, so I think that is actually the final slide, and